Get started. So I finished the vast majority of your homework number 3 as of last lecture. The thing that is most heavily featured on that homework is two-dimensional kinematics, projectile motion specifically. Today what we're going to be doing is going one level deeper and asking why. So at this point we've covered kinematics, which is describing motion. We have the vocabulary to describe displacement, velocity, acceleration in one dimension, in 2 dimensions, using vectors, graphing them versus time, all their interrelationships, constant acceleration equations being a very handy toolkit when you know you have that kind of motion. But we haven't really addressed why. So why do certain things accelerate and other things don't? So that's where we get into the next layer of things, which is Newton's laws. There are 3 of them, and I hope to get through all of them today, and they govern what happens with forces. So a force is something, an influence on the outside world or environment on some kind of object. So there are pushes and pulls that are environmental influences that act on an object. Obviously, the direction of these pushes and pulls are going to be important, so force is a vector. And the 3 Newton's laws kind of tell you about the nature of forces. The first law sets the stage and addresses, well, before you introduce a force and you start poking and prodding an object, what is it that it would do on its own if you didn't have it there? So the first law's job is to establish the natural state of an object. And this is any object. So this is harder to do than it might first seem, because we, of course, live in a world of interactions where rarely is an object being left alone completely. It's always interacting with something. And so we have to be really careful to make sure that we establish this properly, because otherwise we're not going to be able to build forward from when there is some kind of interaction between an object and its environment. In order to start off, I'm going to tell you the wrong answer. Okay, this is the Aristotle's viewpoint. Aristotle came up with this during BC times. That was back when we had quote-unquote natural philosophers, and what that meant is you just kind of think about it, and you think it should be like this, and you can't be bothered by actually checking with experimental evidence how the world really is. And of course, I'm not dredging up something from BC times if there wasn't a reason. If you polled the average person on the street, hey, what do you think motion is like? They're probably more likely to tell you this wrong view that's been long debunked hundreds of years ago by Newton. And so we should talk about what it is and why it's wrong, and why it's so tempting to think that it is correct. So here's what Aristotle reasoned. If an object is at rest, it tends to stay at rest. So you set something down on the table, it'll stay there. But if you slide something across the table, it doesn't seem to like to do that. In fact, it'll come to rest. And so if it's in motion, it also comes to rest. And so Aristotle simply said that the natural state of objects is at rest. So if you put them like that, they will stay there. And if they aren't at rest, well, then they have some kind of innate desire to want to achieve rest. Now, nowadays we know better. We know that the reason why something slid across the surface comes to rest is not because it has some kind of innate desire to do that. It does that because of things that are persistent in our world, like air resistance. It has to move through the air, right? Friction. These are things that are external things that cause the motion to not persist. It has nothing to do with innate desire of objects to not move. It has to do with the fact that we live in a world where when you move, there very naturally happens to end up being things that are working against you. So there's nothing inherently special about being at rest. So let's put in Newton's correction, okay? So Aristotle, incorrect. Let's fix it. There actually isn't that much wrong with it. The only part that is wrong is this part. Okay? This idea that objects innately don't like motion. So it took, Newton had to imagine a scenario that we don't often imagine, we don't see in everyday life. You have to imagine sliding something in a way, and then imagine what if there was no air against, there was no air resistance. What if there was no friction? What would happen? It would go forever. Okay? So Newton simply said that if something's in motion, what it actually wants to do is continue the same motion. So objects do not have any preference for being at rest. They don't even have any preference for being in motion. The only thing that they have a preference for is doing exactly what they were doing, just continuing to do that. Okay? So if they're at rest, they want to stay at rest. If they're in motion, they want to stay in motion. Okay? There's a conceptual name for this idea. It's called inertia. So inertia is this idea that objects like to keep doing what they are already doing. That's it. That is Newton's first law in a nutshell, that if you leave an object alone, it will keep doing what it's already doing. Okay? If you need some evidence of this, I can point to a number of real-world situations. Let's say you're sitting at rest in your car, so your body's at rest. Your body's at rest, so it wants to stay at rest. So what happens when you hit the gas pedal? Well, the car accelerates from underneath you, and then it feels like you're getting thrown back in your seat. You're not really. It's your body wants to stay at rest until the car seat says, hey, let's do something else. But you perceive it as getting thrown backwards. Okay? It's really your innate desire to stay at rest until you're told to do otherwise by getting hit in the back of the head by the car seat. But let's say you're now going cruise control. You're going 100 miles an hour down the straight road. Now that's your state of motion. That's what your body wants to maintain. Okay? So it will gladly maintain exactly that motion, but then if you see something on the road and you hit the brakes, now you feel like you're getting thrown forward. It's not really that you're being thrown forward. What's happening is your body wants to maintain that motion until your seatbelt says, hey, we're not doing that anymore. So it's not that your body wants to stay at rest. It's not that it wants to stay in motion. It just wants to continue to do whatever it is that you were doing a moment before. It wants to do that a moment after, and that's what it will do unless it's told to do otherwise by some environmental influence. Okay? So that is the concept of Newton's first law. And I should mention that this can all be captured by a single statement. Okay? When I say the same motion, I mean everything is the same about it. There's no changes that spontaneously happen. It has to be the same speed and the same direction. Everything is the same. Nothing can change. And so the only thing you can have is a constant speed straight line. That's what this is. Constant speed, constant direction. That's the only kind of motion you can have. Now, we have a quantity which packages up speed and direction. It's called velocity. So a fancy way to say this, now if you understand that velocity means both things, is to say this is a constant velocity state. And I should point out that when you stay at rest, that happens to be a constant velocity state where that velocity that you're doing constantly is nothing. So constant velocity actually captures the entirety of possibilities. So if an object is left alone, it will have constant velocity, either zero constant velocity, meaning it's at rest, or non-zero constant velocity, which means It's stronger than just constant speed. It's constant speed and it's a straight line. Okay? Now, can we observe this in the real world? Yes, we can. I'll show you several scenarios where this comes up. For instance, what if I set a block down on a table or a book or something like that? I place it there at rest, it stays at rest. So its velocity is constant, it happens to be a value of 0. So it stays at rest. Now that does not mean that this object is completely separate from the rest of the universe. It actually does have environmental influences. There's actually two. Gravity exerts a pull on it, so that of course if the table weren't there, it would start to fall down. But there's also another environmental influence, and that is the support force from the table. I'll call that n vector to anticipate later, because a support force can also be called a normal force. Okay? So there are two things that are actually acting on this from the outside environment. If I were to tally the total number of forces, I should say there are two forces. But here's the thing. Those two forces kill each other, and so they might as well not have even bothered. Okay? So it's like if you have a rope lying on the ground and it's staying at rest, it's either because nobody's touching it, or you have 5 people pulling on it this way and 5 people pulling on it the other way, some tug of war where nobody wins. So these two forces kill each other, so they might as well not have even bothered. And so what we really care about, if we are to consider an object quote-unquote left alone, is that it has no overall force acting on it. Okay, so we call this an overall or total force, or more commonly, a net force. So even though there are two forces on this thing, the net force is 0. That is what allows the inertia of the object, its desire to stay doing what it's already doing, to actually persist. So it stays at rest just the way you put it there. It'll stay that way. So it's no different really than if I took this object, whatever it is that I set on the table, I'll go out far into the vacuum of deep space, and I'll set it down here. These are stars, by the way. It's just floating out there, far away from anything. So this, we could say, there's no forces at all, right? There's no planet around to pull on it, and there's also no table or whatever holding it up. And this also has 0 net force. So this would also just stay in place. So these are both identical for all practical purposes. Both of these situations, there's no net force. You can either have no forces at all, or you can have 17 forces acting on it from the outside world, which all kill each other, so it doesn't matter. They might as well not have bothered. Okay? So the Newton's first law, if you want to see it written out, if the net force on an object is 0, then its velocity is constant. Okay? That's the short form of it. All right? So if there is no overall or net environmental influence, then we can appeal to inertia, this idea that it will keep doing whatever it is it's already doing. Now, I think that the at-rest thing, people just naturally, it's like more okay that the net force is 0 when it's at rest. But let me make sure to show you a situation where we have an object moving at a non-zero constant velocity. So let's take a car under cruise control, going down a straight road. Okay? So this car has a constant velocity. Might be 100 miles an hour in a straight line. So let's analyze the situation. Well, it certainly has environmental influences. The force of gravity still pulls down on it, but the surface it's on supports it. So those two kill each other just like before. But, of course, the things that you encounter in the real world is that when you're moving, there tends to be forces acting against you. Air resistance, friction, stuff like that. So I'll just write those down. Force of air resistance, etc. Things that tend to slow you down. So if that is to be not an overall or net force, you need to apply some kind of forward force. So you turn your car on, you have your forward force. Not going to talk about the exact details. Let's just call it the force that is applied by the engine, right? The car has to be running, okay? So those two forces can kill each other. When you turn on cruise control in a car, what you're basically doing is requesting that the forward propulsion force is exactly canceling the backward force. This is where the common misconception is that isn't the forward force just a little more than the backward force? No, they're exactly the same. The thing that keeps it moving is its natural tendency to want to keep doing what it's already doing. Okay? So make sure you understand here that the net force here is still 0. It's the car's own inertia that will keep it going at 100 miles an hour in a straight line if it's left alone by the outside world. So even though we have 4 or more outside forces, they're all still canceling. The net force is 0, and that is what allows this constant velocity to be maintained. So if we once again went out, took a spaceship to deep space, we threw the car out. We threw the car out the airlock at 100 miles an hour, and it looks like this. Here's the stars around it. Here's the velocity. So there's no gravitational pull. There's no upward support from a surface. There's no air resistance against the motion, so we don't need to turn the car on to apply any forward motion either. Not that it would have any traction anyway, right? So this is the case, again, where your net force is 0 because you have no forces at all. But it doesn't matter that you have 4 or more environmental influences. If they all cancel, then we get to see this natural state of motion right here on Earth. Okay? We get to see this state of just continuing to do what it's already doing. Okay? That is Newton's first law in a nutshell. Again, this is the most compact way to write it, and I prefer that. It does require you to understand that net means overall force. It doesn't mean that there can be no forces at all. It just means that the forces you have are all killing each other. And it does also require you to remember what velocity means. Velocity is stronger than just speed. It's speed and direction. And a constant velocity could be 0, so you stay at rest, or non-zero, where you stay at a constant speed in a straight line. That's the most short form that I can give you to write it. It requires you to have that understanding. You also hear the most long-winded way you could say it is this. And I'll give you the statement. Let me take a breath here. An object at rest will stay at rest. An object in motion will stay in motion at a constant speed in a straight line unless acted upon by a net outside force. That is the unrolling it all, okay? But that's all in here, okay? Are there any questions on that before I get to the second law? Yeah.
So going back to that example about the cruise control, so like you said, I find that a little hard to understand because I feel like the force going forward should be a little more than the force acting backwards, but you're saying it's net and it cancels each other.
Yes.
So if you were going at 40 miles per hour and you set your cruise control at 100, so until it increases, it's still going to move, and then once it hits that.
Well, usually cruise control, you can only set it at the speed you're at. So I'm assuming that you are telling your car that whatever I'm doing right now, please maintain it. Yeah, I don't think there's a car where you can just say, hey, can you go up to under 100 miles an hour and stay there? That seems dangerous. And cruise control, if you don't use cruise control on your drives, is when you're going at it doing something and you hit the button to say maintain this.
Okay, so it just balances out the backward
Correct.
forces.
And then this thing, the reason why this continues to do exactly what it does is because of Newton's first law. The idea that an object will naturally continue to do the exact same thing that it was already doing if the environment overall doesn't tell it to do something different. So you have to really get into your head that there's nothing special about being at rest. Being at rest or being in motion is completely equivalent. They're both states where you continue to do exactly what you're already doing. Okay? Okay. Any other questions before I do the second law? Okay, so the second law really just follows very naturally from this. The second law says if the net force on an object is not zero, okay, so you have some kind of overall force from your environment. You have either one force or you have 17 forces which don't all kill each other. There's a little left over. That's your net. If your net force isn't zero, well, your velocity won't be constant anymore. Okay? And luckily, from kinematics, we have a quantity whose whole job is to describe when the velocity doesn't stay constant, it evolves. What is that quantity? Acceleration. So there is some connection between applying a net force on an object and accelerating. So that is why things accelerate. Okay? Now, it's not just we know what acceleration is, we know why things accelerate. Things accelerate not because they get it in their own heads to do something different. Inertia is the guiding principle of any object. It just wants to keep doing what it's already doing until it's told by the outside environment, hey, I want you to do this instead. So if you apply a net force from the outside environment, that is what causes an object to accelerate. In fact, let's go ahead and write down the third ingredient. The third ingredient is the mass of the object. That right there is the equation which gives Newton's second law. And I do want to point out that the second law does actually subsume the first law. If you look at this equation, if F net is 0, then the acceleration is 0, which means the velocity is constant. So Newton's first law will account for if the net force is 0 or if the net force isn't 0. Okay? So that right there, here, Newton's second law in the box, is actually contains all the information we've discussed so far. So let's take a look at its features. Okay? The third ingredient is the mass of the object. Okay? So this is the mass of the object. This is the acceleration of the object. This is the net force on the object from its environment. This equation can actually help us to find what is the units for net force. I guess let's do that first. So of course we have to have a dimensionally consistent equation. And so mass in SI is measured in kilograms. Acceleration is in meters per second squared. And so the units of force are kilogram meters per second squared. We abbreviate that bundle for our first composite unit with its own name. We call it a Newton, or capital N for short. Okay? So this is what I call a composite unit. A Newton is not really its own thing. It's a convenient abbreviation of kilograms, meters, and seconds grouped in a particular way. Those are the fundamental units we discussed on day 1. So let's take a look at what this law is saying. Let's say I have a particular mass like this, and then I have a bigger mass. And to both of these objects of different masses, I'm going to apply the same net force. So the same amount of effort influence from the outside environment I guess I'll go ahead and draw it like this. I'll try my best to draw the net force here the same length. To the best of my ability, I drew those two the same length. So that's the equivalent, of course, of F net being a fixed value. So I'm applying the same net force to both of these as kind of a test case. But on the other side, it's the product of the mass and acceleration that has to multiply to this value. And so you can see, if I have a small mass, the acceleration has to be large. And if I have a large mass, the acceleration has to be small. Otherwise, the product can never be the same number. Okay? So what we find is that even if we apply the exact same influence from the outside world and net force on different things, we're not going to get the same reaction. We're not going to get the same change. Even though everything will react to this influence, they don't react equally.